This video will introduce the series on the basic knowledge of the spectroelectrochemical method, Chapter 5, Optically Transparent Thin Layer Spectroelectrochemistry, Part 2. Summary of this chapter, introducing the non-ideal behavior of the Nernst plot. 1. Spectrally overlapping, chemically uncorrelated redox systems, presented in this article. 2. Chemically correlated redox couple, which will be presented in the next article. First, let's briefly review the previous introduction to the method of determining the quantitative electrode potential and electron transfer number by spectroelectrochemical measurements. For a reversible reaction, the electrode potential can be expressed by the Nernst equation. Obtain the absorbance when it is completely oxidized by spectrum measurement, AO. Absorbance when completely reduced, AR. Absorbance at any intermediate potential, AI. The ratio of the concentrations of the oxidized and reduced components of the solution can be expressed by the following equation. The absorbance at the intermediate potential of the reversible system at electrolytic equilibrium was measured at different applied voltages to obtain the corresponding RE value, and the applied voltage was plotted against log of RE, to obtain a straight line. From the slope of the straight line, the number of reaction electrons N can be calculated, and from the intercept of the line, the electrode potential is obtained. Electrochemical measurements alone make it difficult to measure the electrode potential of quasi-reversible reactions and biological redox systems using a mediator, but spectroelectrochemical measurements and Nernst plots give the number of reactive electrons and potential. Ideally, the Nernst plot should be a straight line, and this is the case for many systems, but in some cases, deviations from the straight line have been observed, one of which is due to the overlap of the spectra of two or more redox substances in the solution being analyzed and the variation of each spectrum within the potential range under study. The second is the synergistic or interrelated nature of the different redox, which will be discussed separately below. For non-ideal behavior of the Nernst plot. Spectrally overlapping, chemically uncorrelated redox systems. Considering the simultaneous existence of several uncorrelated redox systems in the solution, the Nernst equation for the half reaction of component I can be expressed as concentration of oxidant half reaction, equation 5.1, where theta E is defined by the equation 5.2. According to Beer's law, the light absorption at any potential is calculated using the equation 5.3. Where epsilon OI and epsilon RI are the absorption coefficients of the oxidized state and the reduced state of component I, respectively, and the limit light absorption of the oxidized state and the reduced state are respectively absorbance when completely oxidized and absorbance when completely reduced. For the total of the concentration of the oxidation state and the reduction state of each component at any potential is the limit concentration of the component Ci*. For any potential, the total of the concentrations of the oxidized and reduced states of each component is the limiting concentration of that component Ci*. Substituting oxidized and reduced concentration of component I half reaction, then the absorbance of the system at equilibrium can be expressed as the equation 5.6, then combining the equations to calculate the light absorption of multiple components. The value of RE is rewritten as the total of the total absorbance of each component measured at potential E at reaction equilibrium minus the absorbance of each component in its fully reduced state. The ratio of the sum of the absorbance of each component in the fully oxidized state minus the total of the absorbance of each component measured at potential E. For convenience, the difference between the absorbance of oxidized component I, in the fully oxidized state and the absorbance of reduced component I, in the fully reduced state is expressed as delta AI. For the figure 5.1. In the graph, the applied potential for a two-component system with different redox-type quantitative potentials and spectral behaviors. For comparison, the applied potential range and the two-type quantitative redox potential are concentrated in the vicinity of 0 mV. The influence of redox potentials with different potential is shown in figure 5.1a. As expected, when the two components have the same potential and electron transfer number, the resulting Nernst diagram, curve A, is a straight. However, When same potential and electron transfer number are not equal, it deviates from linearity. The larger the difference between the two equation potentials, the more significant the deviation is. Therefore, according to the usual Nernst plot, fitting these data to linearity as per the usual Nernst plot will produce measurement error of the potential and the electron transfer number. The intercepts of the extension lines of the two straight lines in the figure on the y-axis can be used to obtain the quantitative potentials of the two electrochemical redox pairs, and the slope of each straight line area represents the number of electrons transferred per electrochemical redox pair. Figure 5.1b shows the effect of different electron transfer number on the simulated Nernst plots, although the curves have the same values of the potential and absorbance as in figure 5.1a, but the shapes of the curves are very different. Fitting these simulated responses to conventional Nernst plots will yield larger deviations from the measured values, and the slope and intercept of the two linear parts of the plots provide the respective potential and electron transfer number. For the figure 5.2a shows the effect of the relation ratio of delta A2 and delta A1, on the Nernst plot for the change in absorbance of delta A for the oxidized and reduced states for different components, with two equation potentials of -75 mV and 75 mV, respectively, and electron transfer numbers, 1 and 2. The inflection points of these F-curves depend on the ratio of delta A2 per delta A1. The shape of the Nernst diagram is mainly controlled by the redox pair with the larger absorbance change delta A when the delta A2 per delta A1 term is controlled by the second, curve A, redox pair, east 2 degrees equals 75 mV, or the first, curve E, redox pair, so that in the limit, curves A and E, for example where the change in absorbance of one redox pair is much greater or much less than the change in absorbance of another redox pair, fitting the Nernst plot to a straight line will allow the values of E1, O line and N to be determined more correctly for the redox pair with the larger delta A. For two redox potentials fixed at 0 mV, N1 equal 1, N2 equal 2 and large variations in absorbance, the simulated Nernst plots are very close to a straight line and the simulated data give values of electron transfer number N between 1.0 and 2.0, depending mainly on the magnitude of the contribution of each redox pair to the total absorbance, with the equation potential very close to 0 mV. Figure 5.2b shows the two redox pairs each with different electron transfer numbers. In the limiting case, the slope and intercept of the Nernst plot are approximately related only to the redox pair with the larger delta A value. In the limit, the slope and intercept of the Nernst diagram are approximately related only to the redox pair with the larger delta A value, and the slope and intercept of the respective asymptotes can be used to obtain the respective electron transfer number N and the equation potential values for both pairs with little change in light absorption. The thin layer spectroelectrochemical experiments and their simulated responses for mixtures of potassium ferricyanide and otoluidine are shown in Figure 5.3 and Table 5.1. Potassium ferricyanide and otoluidine were chosen because they can represent spectrally overlapping and well-characterized, chemically uncorrelated spectroelectrochemical systems, and in addition, these redox pairs provide a convenient experimental pair for assessing the validity of chemically uncorrelated redox system models. As shown in Figure 5.3, the agreement of the model with the experimental results is evident, and the results of the mixture studies for EO line and N values are also consistent with the measurements when they are present separately. Table 5.1 shows the Nernst graphical analysis of the mixture of potassium ferricyanide and otoluidine. The average formula potential and electron transfer number for otoluidine are 663.6 plus minus 2.3 mV versus silver chloride and 2.02 plus minus 0.19. Here the experiments A, B, C and D, which are consistent with the reported values of 659 mV and 1.9, as are the results for potassium ferricyanide. Finally, if the experimental data in the presence of a single component are analyzed in the two-component simultaneous mode described above, the EO line and N values, for the redox pairs that make up the major component, showed in the experiments 1 line and 2 line, are consistent with the results of the usual Nernst analysis, showed in the experiments 1 and 2, but E20 line and N2, in the experiment 1 line and E10 line and N1, in the experiment 2 line are not significant. 5 variables, E10 line, N1, E20 line, N2 and delta A2 per delta A1, can be obtained from the experimental data measured for the mixtures. This concludes the fourth part of the series on the basic knowledge of the spectroelectrochemical method, optically transparent thin layer spectroelectrochemistry, Part 2.